everyone, and welcome. Very excited to talk about this topic of optimizing linear layers to accelerate inference. Basically, we are going to talk about things like quantization and low-bit multiple kernels and stuff like this. I actually cannot see anything. I'm just like seeing my slides. So feel free, if you have any questions or something like that, just feel free to interrupt me. But I cannot see anything in the chat.
Yeah, I can bring up any question if it's okay.
Yeah, perfect. Feel free to interrupt me. Like, there's no problem. Like, any question is welcome. So for the overview, we're gonna start off with the introduction. So gonna talk about why quantization is important and how to use it to accelerate inference. Then we are gonna talk about writing low-bit multiple kernels, because there are actually different types, and depending on the situation, you might need to use a specific kind of kernel. So we're gonna like go through 3 basic kernels, how to write them. Then we are gonna talk about integration and benchmarks, because there's a lot of stuff to keep in mind to actually be able to benefit from using these multimodal kernels in a real-world application, let's say in VLLM or something like that. So there's a lot of stuff that needs to be done. And we are going to take a look at some benchmarks across some different GPUs. Then we are going to finish off with Q&A for more questions. So let's start. So as everyone knows, machine learning models are getting very, very large. And running these models takes a lot of GPU memory. So for example, like a 7TB model would take roughly 140 gigabytes of GPU memory as FP16. So so even if you have an A100 with 80 gigabytes, you're not able to run it on a single GPU. And obviously everyone knows GPUs are very expensive, especially for GPU poor community. So this actually led to a lot of innovation, and mainly it pushed people like to think about how to compress the models to make them work with consumer GPUs. So that's how quantization in the context of LLMs started to get like a super, became a very hot topic. And right now everyone is using some kind of quantization, either to reduce VRAM usage or to accelerate inference, or both. And obviously things are much worse for training. So honestly, like without quantization, I don't think LLMs would have become this popular. So it's actually a very, very important and hot topic, as I said. So quantization is especially interesting for transformer-based models, because what happens is that most of the weights are actually in the linear layers. So in contrast, like to convolutional neural networks, where like most of the weights are basically like in the last classifier layer. So things in transformers are more interesting because the models are very large. Most of the weights they are in the linear layers. And most of the compute is actually in the linear layers and the attention models. And the thing about the attention is really depends on your context size. So it really becomes an issue when you have a very large context size, but the linear layers are always there. So like either you're using a small context size or a large context size, like linear layers are always a bottleneck. So that's why it's interesting to quantize them. So you can quantize the weights to reduce VRAM usage. And this also makes inference faster in what is called memory bound situations. So this is where you have your batch size like quite small. You can quantize also the activation. So you have both the activations and the weights quantized. So this is typically you usually do it like to accelerate inference for compute bound scenarios. So this is basically your typical situation where you're serving a lot of requests and you have a batch size of like, let's say 64, for example, 128. And you can also quantize the KV cache to reduce VRAM in the context of large context size. So basically, transformers plus quantization, this duo just works really good because like not only you can reduce VRAM by a lot, but you can also make everything run faster. What is quantization? Let's get back to the basics. So quantization is basically just a compression approach. And basically all it does is just it reduces the data bit precision. So think about it as reducing the number of bins to represent one element. So let's say you have floating point, 16-bit floating point, and then you map those values. If it's, let's say, int 4, you will map it into values between 0 and 15, right? So you have 16 bits, 2 to the power 4. So all it does is just reduces the number of bits per tensor, and this reduces the storage. So by itself, it doesn't make anything faster. So it just reduces storage. There's a lot of challenges here, obviously, because compression, it's a lossy compression step. So obviously, we want to maintain high quality of the outputs when we quantize these weights or activation or both. So this is more related to the choice of the quantization algorithm. One thing very important to keep in mind is efficiency in first, like in the step of when we quantize the model. So we don't want something that will take 16 GPUs to just quantize a 7P model. But we also want the inverse operation to be very fast. So at runtime, we want to be able to dequantize this weight very fast. So this is very, very important because if the inverse operation is very slow, then we cannot benefit from the speed up that quantization will bring. So obviously, we could benefit from the reduced VRAM usage, but we will not be able to make things faster if the inverse step, which is the quantization, is slow. So there are different types of quantization. Most popular ones, which is like almost what everyone is using, is a linear quantization. And what that means is that the dequantization step is just a linear operation. So you have some scaling zeros. We're going to talk about this later. But basically, you can do that in a single instruction. So multiplication and addition. And that's like the simplest way of doing quantization. There are other more advanced approaches that they use, for example, like some lookup table, some Hadamard transform, like some other stuff. So usually these nonlinear quantization methods, which are a little bit more advanced, they tend to give better quality in terms of lower bits, like 2-bit, like 3-bit, this kind of stuff. But the issue is that the dequantization step is more complicated, so you don't get as much speed up as you will get with the linear quantization. So linear quantization is basically the fastest thing that you can do because it's a single instruction. In terms of activation quantization, so like mostly what people use right now is some kind of linear quantization. So it's usually symmetric. And the symmetry could be like channel-wise, or it could be like you do it by blocks. So I'm going to talk about this block processing later. But here again, like there are also like some more advanced methods to do it. But pretty much 99% of what people use right now is some kind of linear quantization. So for 4-bit especially, like you don't need much more than that. Like you can really make it work with high quality. So for 4-bit and 8-bit, when I go like lower bits, like you need probably like more advanced stuff to do this. But basically here we are, like for the rest of the talk, we are going to focus only on linear quantization. because it's the simplest and the most used way of doing quantization. Yeah, so linear quantization, as I said, is very simple. The quantization step is basically a linear operation. So you have what is called a 0 point Z and a scaling factor. So when your zeros are 0, we call it symmetric. When your zeros are non-zeros, we call it asymmetric. But basically, you basically have, for a set of weights, you have a single scalar and a single 0 point. So if you do it channel-wise, so let's say your weights are of size out features by in features. So you basically, for each row, for example, you could have one 0 point and one scaling factor. So this usually works quite well for 8 bits, but when you go to lower bits, you need to use what is called grouping. And it's essentially what you do is that instead of doing it for each row, you basically do it for blocks. And these blocks, they have a size of let's say 64 or 128. So this is what it called group size. And essentially what you're doing is just reshaping your matrix. And for each row, you have one scalar and one 0 point. So this is pretty much what it's doing. And so methods like GPTQ, AWQ, HQQ, basically they work the same way. The only difference is that they just have different ways of estimating the 0 point and scaling factor in WQ. That's pretty much it. But the formula to dequantize the weights is basically the same. And yeah, as I said, they are just different algorithms to figure out what is the best parameters that minimize the error. But this is the formula that we are going to work with. And yeah, so at this point, so we have our weights. Let's say we used some, let's say AWQ or GPTQ or whatever. We got our WQ, Z, and S. But at this point, we need to store this WQ, because if it's 4 bits, we need a way to actually store it as 4 bits. And the problem is that there's no native type as int4 or int2. For the moment, there's nothing like that. In PyTorch, for example, the lowest you could go is uint8 or int8. So basically, we need a way to store this 4 bits into the actual format that will actually take 4 bits in memory. And the way how we do this is called bitpacking. And bitpacking is essentially a trick to use native D types to store data which is not in a native D type. It's kind of weird, but it actually works. And basically the idea is that let's say in PyTorch you have your int8 and your weights are 4 bits. So what you can do is to store two 4-bit elements in one single 8-bit torch element, for example. Or you could use int32 or int32. And in this situation, you could put 8 4-bit elements in one single int32. So and this transformation is actually very efficient, because you can just use some shifts and some bitwise operations. So it's just two bitwise operations when you're quantizing, when you're packing in 2 bitwise operations when you're dequantizing. So it's not very heavy operation. And it's also lossless. So it's not you're not losing anything at this point when you do this. It's just you just change the way how data is presented. So basically here at this point, you run your algorithm so you started with W, the weights, your original weights, FP16 weights. You run your algorithm, GPTQ, AWQ, HQQ, whatever. You got your WQ, Z, and S, right? Now you took this WQ and you packed your weights. So you get this WQ packed here. So now your model is actually ready for inference. So this is what you have in in memory. You have WQ packed 0 point scaling factors instead of WQ. So now the big question is how to actually do matrix multiplication with this new representation of data. So because like in the FP16 or FP32 situation, what you would do, like you get your activation. So X is your activations, W is your weights. So basically you just do torch manual XW, you get your output, and you move on. But now you have some complicated formats. So you have this packed data, you have the 0 points, you have the scaling factors, and you want to do a matrix multiplication with this packed data. So the question is how to do this efficiently. So obviously, like the easiest way to do this is just you would say, I'm just going to dequantize this on the fly. So I'm going to take this packed data, I'm going to unpack it. Then I'm going to do minus Z multiplied by S. I estimate the original weight and do just torch manual. So obviously, so this works, but like it's pretty slow because you're not speeding up anything because you're still using the same torch manual XW. And on top of that, you have the cost to dequantize the weights. So what do we need to do to make this operation faster? Is that we need to fuse these operations like the weight loading and the dot product. And the way how we do it is basically we launch this block calculation. So we take our matrix and then we split it into small blocks and we launch these blocks in parallel. And we are actually going to dequantize and do the dot product on the block level, not dequantize the whole matrix. And this is what we are going to talk about later more in detail. So don't worry about it. Just to keep in mind is that the message here in this slide is that we don't dequantize the whole weights and then we call torch manual on the whole dequantized weights. How we do it with chunks, and the chunks are running parallel. So before like talking about this fusing this weight loading and dot product, there's like a very important concept to understand because this concept will actually change the way how we write kernels and the way how we choose the quantization method. So the thing to keep in mind is that let's say you have two setups. So you either, let's say you have the choice between dynamically quantizing the activations as 4-bit and the weights as 8 bits. And the other situations that you just quantize the weights to 4-bit and your activations is 16-bit. So the question here is like, which one is actually better? And the answer is basically, it depends. So quantizing the weights to 4 bits doesn't necessarily mean it's the best way of doing things. It's actually in some situations could run slower. And so these are two typical situations to serve LLM. So let's suppose that you have like few requests, for example, one single user using like a thinking model, for example, like some model that outputs a lot of tokens. So in this situation, like quantizing the weights to 4 bits is probably the best choice here, or even like going lower because basically your prefill is relatively small, but like you're decoding a lot of tokens, and in every decoding step, you're basically just decoding one token at a time, and this is really memory-bound situation. So computer is not the problem. The problem is how fast you can load these weights. So in this situation, you want to quantize these weights as aggressive as you want. The other situation is, let's say you're a big company and you're serving a lot of users, you have a lot of requests. So in this situation, actually, 4-bit is not the right way to do it. Like you need to do something like dynamic quantization, so 8-bit activations, 8-bit weights, because compute is your main concern. Like you're using, first of all, your prefill across the batch is very large. And secondly, even in your decoding step, you're not decoding one token at a time, you're decoding, let's say, 64 tokens at a time or 128 tokens at a time. So in this situation, like the 8-bit version is actually faster, but like it will run slower with lower byte sizes, let's say byte size of 4 or 8. So this is a very important concept to understand, because sometimes you will quantize the models and then you're around them and you're confused. Oh, it's actually slower, but there's a reason why they're slow. It's because of this. So let's take a look at a diagram of to understand this memory bound and compute bound situation. Is there a question?
Yeah, I had a quick question. So in the previous setup, is that typically true for larger models, or like say 70B or something? And is it still does it hold for like 8B or 3B in that sense?
Yeah, it does, because it only depends on the byte size.
Okay, good. Yeah. Because I'd assume in a 70B, like weight loading dominates. So I assume, yeah, makes sense. Thanks.
Yeah. It's if you're like decoding one token at a time, you're basically doing a matrix vector multiplication, and your only concern is how fast you can load those weights.
Yeah. Okay.
Yeah. But yeah, I mean, the general rule is the byte size. It may be oversimplification, but this is basically the most important factor.
Yeah. Thanks.
You're welcome. So let's take a look at this diagram, which basically summarizes what happens when you do LLM inference. So you have your input. So it doesn't matter if it's a vision language model or an LLM. At the end, you have a set of tokens that you process first. When you process first in the prefill phase, you're actually processing many tokens at a time. Because even if you have one single user, in the prefill phase, you still process more than one token. And this is, again, it really depends. So if your prefill is very small, then the prefill, like we see like there's tokens, but like if your prefill is very large, and especially if you're using large byte size, this is really compute bound situation. So in this case, like something like, in this case, if you're using a 4-bit model with 16-bit activations, and even if you have one single user, this part could be still slow actually, because this prefill phase is actually always like, I mean, not always, but like most of the time is compute bound. However, like in the decoding phase, let's say you have finished. So now let's say you have one single user and you're decoding one token at a time. So this is going to be like very fast if you're using 4-bit, for example, and it's going to be even faster if you're using 2-bit or 1-bit. This is mostly memory bound. So I put here mostly because it depends on the byte size. So as I said, like here in this situation, if you have few requests and you're concerned about low latency, this is going to be memory bound. But like if you're, or if you're processing many requests, then this is going to be like kind of memory bound, because it's not like exactly memory bound. It's like it's between memory bound and compute bound. But it's, again, it really depends on this byte size. Like you increase your byte size, you become compute bound. You reduce the byte size, becomes memory bound. So it, again, like it really depends on the situation, which one will be faster. So it's very important to keep this in mind, because the choice of which version you would use depends on your situation. So yeah. So are there any questions related to this, like the choice of quantization and the memory bound, compute bound? Because the next slides are actually about writing the kernels. So if there are any questions regarding this, so it would be good like to answer questions regarding this before moving on to writing the kernels.
If nobody else, I could probably go first. I was just curious, like, is there any? This might be a slightly naive question. That is the bit packing that typically, since there's no support for int4, you do this. Is there any scenario where this is worse than, say, just using FP8, which is already supported? Or where would you make that trade-off? Or is it not that much of a overhead at all in terms of if you write like a very efficient kernel, then it causes no trouble? I hope that question makes sense broadly. Like when would you use, say, something like FP8 or FP4, which is natively supported, compared to, say, something like Int4, where you'd have to do bit packing or those kind of things?
Yeah, that's actually a good question. So the answer is there is some kind of overhead, and your hope is that you can basically kind of hide it by overlapping operations. But there's definitely an overhead. So the thing is that, like with int4, like integers, they are usually faster because like the actual bit packing step. I'm going to talk about it. It's going to be a little bit clearer later because we are going to see how to do it inside the kernel. But there are two steps in the bit like when you're unpacking the weights, like in your kernel, like there's two steps. First one is actually loading the weights, and the second part is doing these bit operations. So the bit operations are actually very fast because it's just two operations. You just do a left shift and then you do an AND. So that part is very fast. So what is and then of course, like you need to do a casting, and casting actually sometimes on some GPUs can be actually slow, a bit slow depending on GPUs. But like the part that actually introduces most of the overhead in the unpacking is actually, it depends on how you do it. But if you do it in a certain way, it will require some copies. I will try to explain this a little bit later because like it will become a little bit clearer like when you take a look at the kernel, because if I can summarize this, like there is some overhead, yes.
Okay.
Yes, and the overhead becomes worse like with floating point types, because integers are actually faster because they are very simple. Floating points are a little bit. So for example, like if you're unpacking FP4 instead of int4, that will be actually slower. It's just because like you need to do more operations to unpack it.
Got it. Yeah, that makes sense. Thanks.
Yeah, you're welcome. But there's like another thing related to the overhead, related to copies, but I would explain that like later in the kernels, like once we take a look at the kernels. All right. Any other question? Just regarding this part, like introduction and memory bound, compute bound, this A16W4 versus dynamic quantization. If it's not clear, I'm happy to clarify it again. All right. So if there's no question, I think we can move on to writing this low-bit mathematical kernels. So we are gonna get a little bit technical here. So like it's the end of the day. I think people are a bit tired, but this is fun. So and hopefully it's going to be very useful. So we are going to take a look at how to actually write these mathematical kernels, and we are going to start off with we are going to do this in Triton, by the way. It's just because like it makes things easier. So the way how we do this, like let's start with the simple matrix multiplication in Triton, like a GMM, like nothing fancy. So there's no quantization here. Basically, what we want to do is math mill between A and B. We get C. And the way how we do it is very simple. It's just that we take our input A, there will be like the activations. The input B, there will be like the weights. We just chunk them into some blocks. and basically like we just loop over the k dimension here. So this way you have 4k in range NumPy k, and basically we just load this chunk, do the dot product, and just accumulate, and then we got this blocks. Pretty simple. So the only thing, so if you're not familiar with Triton or GPU programming, just think about it as you run, like you take a big matrix, you split it into blocks, and you just run these blocks operations in parallel. It's that simple. Like, so here, there's nothing fancy here because here, as I said, it's a simple GMM. There's no quantization here. So how do we take this and actually make it work with this matmu low bit WQ packed in with zeros and scales? So how do we do this? So what is changing here? So first of all, our B is packed data, right? So if it's int4, for example, it will be packed. If it's 2 bits, it will be packed. If it's 8 bits, it's not going to be packed, right? So if it's, let's say, if it's 8-bit activations, 8-bit weights without the scaling, so that would be like this. 2 will be exactly like this. But if your weights are packed, so B here is packed. So first thing that we need to do is to actually load this packed data properly. So there's different ways of doing it. Like my favorite way of doing it is just to play with these offsets. So the way how it works in Triton is that like you build these offsets. So these are like indices of the rows here. So offset k would be like 0, 1, 2, 3, 4, 5, 6, 7, 8. And basically what you could do when you have packed data is just that instead of loading one chunk at the offset k and then like doing a copy. So this is the copy I was talking about because like it's packed, so you need to actually copy it. So if you're storing 2 4-bits in one 8-bit, you actually need to load this chunk and then make a copy of it. You concatenate that. And then with that, like you need to do the dot product. But like one very neat way of doing it in Triton is just you just give it the same offset. So instead of loading 0 and then you copy that block at 0, basically what you do, you divide by the number of elements. So if you have again storing 2 4-bit elements in one 8-bit, so instead of having 0, 1, 2, 3, you would have 0, 0. Etc. So basically, it just duplicates the weights, which is a really cool trick to load this packed data very fast. So this is the first step. So we need to load this data. We need to unpack it. So when we unpack it, like we need to do these tricks. Like this is where the shifts and the end operation we happen. So that's actually very fast. On top of that, we need the zeros and the scales. So we need to load these zeros and scales. So here it's in red, like we load them, and basically we do B minus zeros and multiply it by scales. That's our dequantization step. The better way of doing dequantization is actually B multiplied by scales plus zeros. And the difference is that the first one takes 2 instructions. Second one takes 1 single instruction because like you can make the multiplication and addition in single instruction. So this is basically the difference, is that between non-quantized version and the quantized version. So basically, to summarize just this part, we need to load these packed blocks. So for that, we need to change the offsets. Second thing, we need to load these zeros and scales. And then we dequantize, then we unpack and dequantize. And one thing that is very interesting here to keep in mind is that these zeros and scales here in this block are actually vectors. So so on the k dimension, it's actually 1. And this is very important because of this, like we need to make sure that this block size k is actually smaller or equal the group size. Otherwise, the results will not be correct. And this is one of the small tricks to keep in mind. Like if you're writing a kernel that only supports one block group size, you can hard code it. But like if you're trying to support different group sizes, like you need to keep that in mind because of the auto tuning. I'm gonna talk about this a little bit later, but basically the idea here is that you load one scale per k dimension. Then you load this, and then you're good. So this is actually a working kernel. Like if you copy past this, like it's gonna work. So it's not like just some random stuff. This actually works for 4 bits. One thing to keep in mind is the zeros and scales. So there are different ways to handle them, especially the scales, because if it's grouped, like you have this group size 64, 128 that I have explained before, like you need to load these scales and zeros inside this for loop. Like there's no other way of doing it, in Triton at least. However, like if you're doing it channel-wise, you can actually do it outside the loop. So you can do it like after the loop finishes, which is usually faster to do it that way. If you're doing block size, like blockwise activation scaling, which is like what's used in DeepSeek, for example, like you need to do the loading of the scales basically here, like inside the loop. But it's usually like the scales and zeros, like they are really not a big deal. Like as long as your group size like is 64, 128, like if you go like below like 32, it becomes like it really starts to slow down inference. But if you're like 28, it's actually quite good. The group size here is the choice of the group size is going to slow down inference for 2 reasons. Because the first one is that you're loading more scales and more zeros, right? The second thing is that like because of this block size k restriction, you would only be able to use a smaller block size k, because like there's this restriction on block size k to be able to load like one vector. So the lower your group size is, the worse it will make inference, because not only you're loading more scales and zeros, you're also restricting the block size to smaller values. So that's usually a bad idea to go like 32 or 16. So I'm saying this because like a lot of models that are quantized, they are quantized with the group size of 32. And in a symmetric way. But you can actually get basically the same performance just doing asymmetric with group size 64, and you're going to run it faster. So there's a little difference here. I'm not talking about Blackwell, which supports like this MX FP4. I'm not talking about that. I'm talking about like the traditional way of doing int for quantization. Usually like lower group size makes things slower. All right. So this is, I already talked about this. This is just a trick like to load these blocks. One trick is just you play with these offsets. The other way of doing it is that you actually load the packed block and then you just duplicate it, which is like, it's usually slower to do it that way. So this is the preferred way of doing it. And the dequantization and unpacking, the unpacking is, as I said, is just like some shifts, right shift and operation, and dequantization, as I said, like you can do it in a single instruction with the FMA format. So you would do B multiplied by scales plus zeros. All right. So now we actually saw like how to do this GMM, which is a good way of doing compute bound scenarios. But like if you use this for decoding, it's going to be like horrible. Performance will be very bad. So we actually need different algorithms for decoding. So if you're decoding byte size of 1, so you're decoding 1 token at a time, like we are going to use another algorithm. It's called the GMV kernel. And basically the way how you do it is you don't do any loop and you just launch more programs. And these programs will use basically atomic addition to load all the partial dot products. And also here, so here, like the one thing here is to notice that for the dot product, I use tl.sum, but here I use tl.dot. So tl.dot is going to use tensor cores. But here, like, we don't need tensor cores, actually. First of all, because our batch size is 1. And secondly, to use tensor cores, like, you need a minimum group size, like you need a minimum size, which is in Triton 16. So if you want to do this with tensor cores, first of all, like, you need to load and pad with zeros. Then you're going to do a dot product, and then you are like, because there's like, you cannot select the first row in Triton, so you need to do another tl.sum over the x-axis to get the final vector, which is like just much slower than this. So like, there's really no point here, like, to do to use tl dot with tensor cores, like, because that's not the problem. Here the problem is that, like, it's not the computer's problem. The problem is that we want to load these blocks like as fast as possible. The way how we do it, we launch more programs, and the reason why we can do this is because our batch size is very small. So we can actually launch a bunch of programs, and everyone is just loading a chunk, and then we use this atomic addition. So atomic addition, if you're not that familiar with, is basically just accumulating. So you initialize your output with zeros, and each program will basically calculate a small chunk, and then it's going to add it back with atomic addition. So this is for group size 1. Sorry, not group size 1. Sorry. So for batch size 1. So this is when you're decoding 1 token at a time. And the other algorithm, which is used when, like, you have batched inference, is called the split K GMM. And it's actually very similar to this GMM here. But what we are going to do is just launch a little bit more programs because our batch size basically allows that. So it's a very small change, is that just you have this split K parameter, which is like 2 or 4 or 8. But typically it's like 2 or 4. And basically we're just going to launch like twice more programs along the K dimension and do like, so split K is something between GMM and GMV. So it's just like it's looping over the K dimension like here, but we are actually splitting this for loop into more programs. So there's like a really minimum changes that you need to do here. So you just introduce this split K here, you change the index for the scales and zeros, and at the end you just replace this. So here we have tl.store. So in the split K, we do tl.atomic add. It's very similar to GMV, and we need to initialize the output with zeros. Yeah. So at this point, we saw actually three algorithms. So we saw the low bit GMM, we saw the low bit GMV, and we saw the split K GMM. So 3. And the reason why we need to do this is because each one of these algorithms is fast in certain situations. So typically what we are going to do, we are going to use this GMM always for the pre-fill phase, because usually we have a lot of tokens. But like for decoding, like we are going to check if our batch size is 1, like we are going to use the GMV. If our batch size is like between 2 and 64, we are going to use a split K GMM. So that's how I personally do it, and it's like the best configuration I found, like across different models and different GPUs. So let's take a look at some Matmul benchmarks. I usually don't like to take a look at Matmul benchmarks alone, because like it doesn't tell you a lot about the end-to-end performance, like in actual inference, but it's actually useful in this situation. So So here, like you have, on your x-axis, you have a byte size, and this is the win A16 W4, so 4-bit quantization with group size. And on your y-axis, you have the speed up with respect to FP16. So when your weights are not quantized. So here, like what is interesting, obviously this is what you would expect if your kernel is working properly, is that like when your byte size is small, you will get like a big speed up. So here, like 3.5 for 4-bit, like max. And then the speed up would go down as your byte size increases, because here you're actually you're compute bound. And there's this situation here is that like normally this prefix would actually be slower than 1 on some GPUs, but specifically for the 4090, because it's using FP16 accumulations, is slightly faster than 1. But like the main goal here, just to show you, is that the speed up is not something like that is constant. It's the speed up depends on the byte size, and it also depends on the algorithm. So the one in red, for example, it's really good kernel for decoding. But as you can see here, like when the byte size is large, like it becomes like super slow. And what would happen is that if you use that kernel in the context where you have a very, very large prefill, it's going to spend a lot of time just doing that prefill. But the decoding would be very fast. So that's why it's important actually to design like different kernels for different situations, and then you just dynamically decide based on the situation, oh, I'm going to use this one, or I'm going to use this one. So very quickly, small comparison with 2-bit version. So obviously what we would expect is that when the byte size is small, we need to see the 2-bit like faster than the 4-bit, and this is exactly what happens. So here, like for the 4-bits, like 3.5 faster. You bump it to, like with 2-bit, it becomes like 3. Sorry, it becomes like 5 to 5.5. But then again, like the speed up like goes down. Obviously, and the same story here. Like if we didn't have FP16 accumulations here, like the speed up would be slower for larger byte sizes, even though we are using 2-bit weights. So like very quickly, I'm not gonna go through this in detail, but basically this slide is just about like how do you support like weird odd bits, like 3 bits and 5 bits, because like if you try to bit pack like 3 bits in 32-bit, like you can put 10 3 bits, but then like you're missing 2 bits, like. And also it makes like other things weird, because like you're working with 10 elements which are not powers of 2. So it makes like the whole thing like a kind of nightmare to deal with. So one of the easiest way of doing this is basically you can just split it into friendlier powers of 2. So basically, like for example, like 3-bit, you can split it into one matrix is 2 bits, the other one is 1 bit. If you have like 5 bits, you can split it into a matrix that is 4 bits. And another matrix that is 1 bit. And basically what you do, you actually, then you work with two matrices, and then you basically, when you unpack it, just combine them, and then the rest is basically the same. Like the scales and zeros, they don't change, but it's just the way how you unpack changes here. And this is exactly how you would expect. Even with this double packing, at least with Triton, it just works fine. So here, the 3-bit is faster than the 4-bit, and the 4-bit is faster than the 5-bit. So this is exactly what we will expect. So even with this double packing, you still get like the benefit of having lower bits for smaller byte sizes. All right, so so at this point, basically we saw these algorithms, like how to write the low-bit mathematics. First of all, we saw quantization, so going from unquantized weights Then you get these WQ zeros and scales. Then we saw, okay, like how do we figure out like how to run this faster? So then we saw, okay, like there are actually different ways to make it faster because like you need different kernel for different situation. Then we went through the different kernels. So we went through the GMM, the low bit GMM, we went through the GMV, we went through the split K. So now we are actually going to talk about like how do you actually make this work with the like end-to-end inference? Because like just writing the kernels alone is actually not enough. Like you need to do some other stuff. So the first thing, as I said, like kernel scheduling. So you need to pick the right kernel based on the right part size and the right settings. Actually, here I just showed you 3 kernels, but actually, depending on the GPU and depending on the quantization settings, you might need to write other kernels. So I didn't talk about it here, like because like we don't have the time, but if you want really the best performance, you need to actually write different versions, and you basically decide based on the settings which one you need to use. Auto tuning, so you need to take care of auto tuning, which is very important. And it's important for 2 reasons: for performance, and the second thing is auto tuning needs to double check if the parameters are correct, because if you pick the wrong block size K, given a group size, you will get wrong results. So it needs to, so you need like a logic where you run a lot of auto tuning, but at the same time, you need something that always double checks if the auto tuning parameters are actually correct and they are going to work with the kernel. Because if you mess up like one auto tuning parameter, which actually works in a situation, let's say block size K 128 with the 4-bit weights, it will work quite fine with channel-wise quantization, but it would not work with the group size 64. And the reason is because of this situation of like the scales and zeros. Like you need to make sure that you load vectors, but your kernel is not going to crash. It's just going to give output, like wrong outputs. So you need some logic that checks all this stuff. So CUDA graphs is very, very important, especially for these kernels that use this atomic addition here. So especially for this split K and GMV, because there's you need to initialize your weights by zeros, and that kind of like introduces another overhead. So it's very important to use CUDA graphs, because like usually what happens is that like you run this end-to-end inference with these kernels and you're disappointed. You're like, oh, why is it slow? Well, it's slow because there's a cost to launch these kernels first. And for a certain type of kernels, like there's also another set of operations that are happening. As I said, for split K and GMV, you need to initialize the weights by zeros. And that just the fact that you need to initialize the weights by zeros introduces some extra overhead. And use CUDA graphs to hide all of this. You need to make sure that your low-bit kernels, they are compatible with torch compile. So that will allow you to use torch compile in some situations, for example, with VLLM v1. So it requires some work, like typically like packing your forward passing what is called a custom op. And in some situations, when you do this, like you need to write a kernel for activation quantization when you need it. Another thing is that just to win the, like just having the matmil kernels alone, sometimes it's not enough. Like on top of that, you also need to write the packing and unpacking kernels, because in some situations you actually need to unpack the kernels, split the weights. For example, if you're trying to use multi-GPU, so tensor parallel, and you already packed your weights, basically what you need to do is, depending on the way how you packed your data, basically you need to check these weights, unpack them, then split these weights across the GPUs, and then you need to pack them again so they can use the kernel. And you need to do this in a very fast way. So you also need to write kernels for the packing and unpacking. So it's usually it's actually a lot of work, because like it's not just writing one single kernel like this and it just works. Like it's there's a lot of stuff going on, like writing different kernels and all this babysitting with auto-tune and CUDA graph and torch compile and packing. So everything, like you need everything to make it work in like in the end-to-end inference engine. So let's take a look at some decoding performance. I put here like 3 graphs like across different GPUs, and the only thing that I want to show you here is that not the performance that is actually changing depending on the GPU, but it's also changing depending on the batch size. So like you would see that int A dynamic, which is like the green one, is almost always faster than 4-bit weights only after batch size 64, because like it becomes like mostly compute bound. So on the 4090, so this is with VLLM and using Gemlight, which is my library, which implements all these kernels. Like you can see, like the performance is really good, even with the 4-bit weights with larger batch size, which is kind of weird, because this is not supposed to work like this. But the reason why it works like this is because like it's using FP16 accumulation. So on consumer GPUs like the 3090 and 4090, there's a nice trick where you can use FP16 accumulation for your dot product, and it makes like things faster. And also like in the newer GPUs in Blackwell, which is great. However, like the situation is not the same. Like performance is completely different if we check another GPU. So I took like here we have the A60000 Ada. So here at this point, like after 64, like this 4-bit kernel is actually slower than the 16-bit, which is what you would expect. This is completely normal behavior. And the other thing that you cannot see here is that like for small batch size one, like the 4-bit is actually much faster. It's like 3 times faster. But like in this graph, you cannot see it. But that's not the reason why I put this graph. The reason why I put this graph is just to show you like how things actually change with the batch size. So on the A100, this is basically the same story. Like here, actually in the A100, it's actually after batch size 32 where you get like slower 4-bit inference. And the 8-bit is like almost always faster for some reason on the A100. So like different quantization methods, they have different performance, and they have different performance in different situations, and they have a different performance on different GPUs. So that's basically my message here. Yeah, so here I put some resources if you want to play with this. So I put here like HQQ, which is fast on-the-fly quantization. If you don't want to wait hours to quantize a model, you can do it like in a few seconds. There's Gemlight, which is a library implementing all these kernels, all types of like 8-bit quantization, 4-bit, 2-bit, like all the combinations. Docker.io, really nice PyTorch library to run quantization. They also have different kernels. And obviously Triton, like if you want to write your own kernel, you want to experiment with this, Triton is probably the easiest way of writing kernels. And yeah, and thank you very much for your attention. It's exactly 7 p.m. So it's exactly 1 hour.
Yeah, that was a really nice session. Thanks a lot.